suppose K as an attractor is the attractor of a system S1 Sm, therefore we have M maps and M copies, yes, and let gamma be its its intersection graph. So suppose we have self-similar set K and we consider its intersection graph. For example, let it be a von Koch curve, for example, yes? So, can you construct the intersection graph of this self-similar set? Supposing that it is generated by 1, 2, 3, 4 maps. So, let us produce this. So, we have K1, this will be K1, this will be K2, this will be K3, and it will be K4. There are 4 copies. Yes? And they have 1 point, these copies have 1 point intersection, these copies have 1 point intersection, and these copies also have 1 point intersection, so this graph will be a line. Yes. And if we take Sierpinski gasket, here it is. So it's what will be the intersection graph of this set? We'll have K1, K2, K3, K2, K3, and there will be edges between these copies. I also need to remind you one fact which I proved yesterday before we shifted to the construction of examples using IFS style. I proved that the set how it is denoted VRK of X, V rho K of X, which is the union of KI1 IN such that diameter of KI1 IN less than rho and less or equal than rho and K and the sets were okay and less than K I1 IN minus 1, yes. So I mean that we take a point and consider copies containing this point, yes. But these copies whose diameter is less than rho and previous ones are greater than rho. Yes? So these sets form, if you take rho n forming a sequence converging to 0, so the sets V rho n of k of x form a fundamental system of neighborhood system of neighborhoods of x in K. So this is just a technical moment, but we will use it very soon. So if, for example, if I take this point here, right, then this V rho n will be unions of triangles, yes? I take this one and this one, they form V rho, I say 1/4, and this one and this one will make V rho 1, so if this is 1/2, this 1/4, 1/8, and this one form V rho of 1/16, etc. Yes. So this is a good fact. And we will use it very soon. This was the first. So I'm interested when the self-similar set is connected and when it is disconnected. So there was very old, well-known result. If the sum of all contraction, so let Q1, Qm will be contraction ratios of Si. Si, yes? So suppose we have these contraction ratios, so in this case all the contraction ratios will be 1/2, right? This contraction ratio is 1/2, this contraction ratio is 1/2, and this is 1/2. Yes. If the sum of Qi from 1 to m is less than 1, then K is totally disconnected. This is a very simple statement, and it follows on such a consideration. So suppose that K is not totally disconnected, and we have some points x and y lying in some connected component of K. Yes? So we can consider that they are connected by some kind of continuum, yes? Yes. And if these points are connected, then dimension of this set is not less than 1. Because if a set is connected, the dimension is greater or less than 1. Yes? Yes. But if you consider a path, so we have a sequence of copies connecting x and y. But if the sum of qi is less than 1, then I will show it that the dimension of k is also less than 1. And it will be done a little further. Yes. And third statement was the following. Three. If the intersection graph of K is connected, then K is connected. It is arcwise connected. And locally connected. This result was proved by Masayoshi Hata in 1985, his 1985 work. And also this result is explained in Kigami's book, Analysis on Fractals, Jun Kigami's books. Yes, and it also appears in many other places. So I will not plunge into details, but explain what is the principle, what is the idea of proof of this statement. So suppose that the intersection graph of K is connected. Yes. Suppose the intersection graph of K is connected. Then, so we take 2 points in K. For example, x and y. So x lies in some one copy, say K1, and y lies in some other copy. And since the intersection graph is connected, there is a path, yes, from this copy to that copy, which goes through intersections of this copy. So we have such a situation. So we have some K1, and we have X, then K, maybe KI1. And then we have KI2, and then we have some KI3, and then we have KIN. So we have a sequence of copies. First copy contains X, and second copy contains Y. Okay. If this copy pairwise have non-empty intersection, then we can find the points, choose some points in these intersections. Yes? Therefore, we have a kind of path, but this path is not continuous, yes? So this is a path, discrete path, and the distance between the copies is less than rho k. Rho multiplied by diameter of k. Diameter of k, right? Okay. Can we make this path? So this path is just a sequence of of points, and the distance between two subsequent points in this sequence is less than rho multiplied by diameter of k. Can we make it find a more dense sequence of points with pairwise distance between them, so that this distance would be less than, for example, rho squared. Oh, sorry, not qk, q, yes, q. We have so q is maximum of qi. Yes, qk, yes. So it will be q less than q squared of k. How to do this? So consider this copy, yes? And we have some of these copies, and consider the points. It will be xi and xi plus 1. I plus 1 in this intersection. So we can take the preimage of this copy and preimages of this si minus first minus 1 of xi and si minus 1 of xi plus 1. Now we are again in the initial attractor, and these 2 points, since the intersection graph is connected, can be also connected by a change of pairwise intersecting copies. Yes, such that first of them contains this point, and the first contains this point, and the last contains this one. And we take the intermediate points in intersection of this copy. So we came this way, we get a ramification of this sequence, yes, and pairwise distances between points will be less than q squared by diameter k, right? Then repeating these steps, we will finally get a path in k. As a limit, we get a path in k which connects the points x and y. Therefore, we see that k is any 2 points in k can be connected by a continuous path. So k is arcwise connected. Since k is arcwise connected, it's connected too. Yes. But now we look at this statement. And take any point in K and consider neighborhood V rho K of X. This neighborhood is a finite union of images of K. Yes, which have one common point. So we have X and we have several copies which form a raw neighborhood of X in K. These copies are connected, and if we have union of several connected sets having one common point, this union will be connected to, right? I don't see your reaction. Is that right? If we have several connected sets having common point, this union will be connected. Yes? I will be pleased very much if anyone disagrees. And then I will be obliged to prove this, but the proof is very simple. So each point has a fundamental system of connected neighborhoods, which means that K is locally connected. So yes, this is very interesting. There are two sides of these questions. First, are there disconnected but locally connected self-similar sets? Can we construct a self-similar set which consists of several components, for example, from two components? Yes? These components are connected and locally connected, but they don't intersect, of course. Oh, this example is easy to construct. I don't know, maybe I will erase this first line to show it. It will be 1, this will be 2, 0, 1, 2, 3, 4, maybe it's enough. And I consider, yes, 1, 2, yes, 1, 2, and 1, 2, this way. So I want to draw a picture, but it's a problem how to draw it. So I draw one copy. It looks this way. One. Second copy. I don't know why these markers are all black. Can anybody provide me different colors? Is it possible to fetch red or green one? Yes. Okay, but this time I will do this. Second copy will be drawn by this line. Yes. So it will be 0, 1, 2, 3, 4. Now I have a gap. 5, 6, 7, 8. 8, okay, and 9, 10, 11, 12. And the second copy will be this way. Oh, no, sorry. This, and so it will be K1, this will be K2, this will be K3, and this will be K4. Can you draw this picture? Is this a self-similar set? So you see, K1 is K divided by 4, right? Oh, so I'm indebted to you for all my life. Thank you. Yes, okay, K1. K1 is, so we have 1/4 multiplied by K, right? We have a contraction of K in 4 times, yes? K2 is 1/4, so 1/4 multiplied by K, and it is shifted by 1, right? It is shifted by 1. K3 is shifted by 8. 8 plus 1/4 multiplied by K, and K4 is shifted by 9. So we have a self-similar set which consists of 2 connected components, yes? Yes, but these components are straight line intervals, right? So it is disconnected, but the components are good. They are locally connected. So this is one example. So if the attractor is locally connected and contains finite number of components, then intersection graph is disconnected, but all other things are good. And now I want to provide you an example when a self-similar set contains uncountably many connected components, but these connected components are lines, yes, and it is not locally connected at any of its points. Do you know the simplest example of non-locally connected self-similar set? Can you provide me the simplest example of non-locally connected self-similar set? Fantastic. You fill my heart with enthusiasm. Cantor set. So, if you take a square, 3 by 3, yes, and make copies K1, K2, K3, K4, K5, K6, right? K6, sorry. You see? So this will be a fractal square. So it is generated by 1 divided by third homotopy, yes, and also translations to these points. 0, 0, for example, 1/3 0, 2/3 zeros, etc. Yes? If you look at the attractor of this system, we'll see that this attractor is a product of counter set and vertical unit interval. Do you see? Yes. I see that you don't believe me and I need to prove it by experiment. One second. Let me put it here. I will write L equal to, so we have 6, 6, so we have 1/3. Do you see what I write? Yes, it is visible. So I took a program. I don't care too much about this program. I just write one line and it will be enough for me to make a needed object, and if necessary I will erase it. So I take 1/3. So this is a homotopy, and then I multiply it by the union of shifts. So 0, 0, 1, 0, 2, 0, 2, 0, 2, 1, 2, 2, 2. So let us, I don't want to write 6 operator because I can write only 5 of them. So I make it this way. I take first I take 0, 0, union 0, 1, 0, 1. So I have a wrong, yes, of course. Please change the order of coordinates. I 0, 1, and union 0, 2, 0, 2, 2. So this will give us a vertical line, yes, and I multiply it by a counter set. Counter set will be 0, 0 again. To write 0, 0 is very difficult job. I will just write 1 because 0 translation is identity. It was not wise of me to write 0, 0 here too. I write 1, yes? So I economized the electronic ink, and here it will be 2, 0. 2, 0. 2, 0 is the optimal way of. And all this will be multiplied by this set L. Okay? That's all. So this string is completely independent of others, and it will be also evaluated and shown on the screen. under our request. So I apply this. Okay. And let us consider, here you see there is L in the list of possible objects. There are T, K1, K2, K3, and L. Do you see it? This is L. It's a product of counter set and vertical line. I don't know why it... So, if I magnify it at any extent, we'll have the same picture, right? Yes. So, any of the point here has a neighborhood which contains of uncountable disconnected union of vertical lines. Yes. So it is not locally connected. Yes. Neither of its points has a system of connected neighborhoods. So let us proceed further. Let me check. When we need to finish? 10:30. Okay, so we will finish at 10:25. This will be my gift to you. Because the breaks are too short. You cannot recover during such breaks. And me too. One second. Let me look at my plan. Yes. But truly, next topic will be about dimension, because our tale of connectedness came to an end. So we can make a break, and then maybe begin a little earlier. So what is it's 10:30, 10:45. Can we begin at 10:40? Okay. So please relax. Meantime, you can ask me questions.
There is a tea break now.
What?
There is a tea break of 15 minutes, as we have a schedule in our...
Please.
So as it is a schedule, there is a 15-minute break. So class will be started at 10:45 or 10:50. As you said, the class will start.
Please repeat your question.
Sir, I am saying that the class will be started at 11.
Oh, 10:50. Sorry, I suppose that...
Okay.
10.
Because the class is going to start.
I don't understand. This is a break. Break finishes at 10:45, but class begins at 11. It's a contradiction. What?
We have already given 15 minutes to rest.
But you also give up 15 minutes also now.
It's okay.
Okay,
so we begin at...
class at 10:50.
Oh, yeah. Oh, now it's okay. So I will speak about the dimension, and first I will explain box dimension, but there was a question in advance. How to explain box dimension? To explain box dimension, we need to make a whole picture of dimensions. When we consider what is Hausdorff dimension, then we'll understand what is the box dimension. Maybe this way is better than inverse one. So first, there is a lot of names for box dimension. It is called box dimension, box counting dimension, fractal dimension, Minkowski dimension, Kolmogorov entropy, and many other names. Yes. So how it is counted? Suppose we have a fractal. Suppose we have some set, and we cover it by boxes of equal size. Cover it by boxes of equal size. Yes? And we find the number of boxes. So we have let k epsilon is the number, of course minimal number of epsilon boxes covering K. So we define the upper Minkowski dimension or upper box dimension, whatever you like to tell, of K is the upper limit of logarithm of nk epsilon divided by a logarithm of 1 divided by epsilon, as epsilon tends to 0. Of course, there is a very interesting question. We can consider upper limit, we can consider lower limit. At some times, there is a happy coincidence when these two limits coincide, then there will be simple limit. Yes. Of course, there is a temptation to give example when upper limit and lower limit do not coincide, but we will do in some break, not just now. Yes. So, if you take the upper limit, it will be upper box dimension. If we take a lower limit, then it will be lower box dimension. And if they do coincide, then we consider simply a limit of ratio of these logarithms, which gives us the box dimension of K. So it is, this thing is discussed in the book of Kenneth Falconer, Fractal Geometry, Foundation and Application, and I often use this picture. I will enlarge it. So n delta of K and the nk epsilon is the number. So we have a fractal and a number of sets, minimal number of sets of diameter epsilon covering K. They may overlap if you wish. But we need to minimize, then we minimize the overlap. Wonderfully, these sets can be replaced by balls. A minimal number of balls of radius epsilon covering A, K. Or minimal number of boxes which can be placed in different ways covering A, or minimal number of boxes in a grid, or minimal number of circles, non-intersecting circles with centers in K. When we pass to the limit, the difference between this number has some linear coefficients, like if we replace the balls by boxes, the number of boxes is multiplied by maybe by 9, something like 9, or 3 to the power of n in Rn. Yes. But when we pass to the limit, this linear logarithm of this linear coefficient vanishes. Yes, so finally we get the same number, because if you have a limit when epsilon passes to 0, logarithm m multiplied by n k epsilon divided by logarithm 1 divided by epsilon, we just write this way, right? Oh, sorry, logarithm is here up m, and we just write this way. We erase m here, put it here. Logarithm m divided by logarithm 1 divided by epsilon. But this, since 1 divided by epsilon tends to infinity, this disappears in the limit. Therefore, this changes in the size of this and form of these sets make a zero impact on the result of this operation. Therefore, we have this formula. Better to apply this formula to this case when we have boxes in a grid. Therefore, so it was a very good thing for fractal theorists. We take a fractal, put it on a boxed paper, right? Put it on a boxed paper, count boxes, and divide them by logarithm of the size of a box, and we have a very good approximation of its dimension. It's fantastic simplification of all processes, therefore it is used popularly, but sometimes it works well. Sometimes it works well. So let us check how it works in very good and very special cases like this. So I will keep this formula so that we could see it. And now, if k is finite, then the number of boxes is constant, independent of how small epsilon is. Therefore, we have constant n, and this logarithm tends to infinity, and we get 0. So sometimes it is denoted as Minkowski dimension or as box dimension. So we have then box dimension of K is 0, yes, if K is finite. If K is an interval, K is 0, 1, then we divide it into n parts. Each part is 1 divided by n. We have a dimension of 0, 1 is equal to logarithm n. This is divided by logarithm n, which for sure gives us 1. Without passing to a limit, we get this number. So, okay. And if we take, say, counter set, if you take counter set, you know. Yes, you discussed it with Professor Sorab Katyar. Yes, if we have counter set, it consists of 2 to the power of n copies of diameter 1 divided by 3 to the power of n. Yes? Yes? So we have a limit when n passes to infinity, tends to infinity, logarithm of 2 to the power of n divided by logarithm 3 to the power of n, and can be cancelled, and we have a logarithm of 2 with respect to 3. So for counter set is everything is okay. If you think that everything is okay all the time, this is not true. These are specially selected good cases. Yes, when you are a mathematician, or if you use mathematics in practice, you know that almost all cases are bad. There are no good cases. Good cases are created artificially by some wise people. To make a person feel comfortably in this world. Okay. So consider this one very interesting case. I consider K is a sequence 1, 1/2, 1/3, 1/4, and union 0. Right? Oh, sorry. Sequence 0. So we have this sequence 1, 1/2, 0, 1, 1/2, and here we have 1/n. Yes. So let what happens? It's okay. Let epsilon be equal to 1 divided by n squared. I don't understand why it sometimes it doesn't catch, it doesn't see me here, and here it sees me. So let epsilon be 1 divided by n squared. Then we have the boxes of the size 1 divided by n squared cover all numbers from 1 to 1 divided by n minus 1. There will be n minus 1 such non-overlapping boxes. And here we have also n non-overlapping boxes, right? So the number k n of k 1 divided by n squared is equal to 2n minus 1. And if you take logarithm 2n minus 1 and divide it by 2 logarithm of n, yes, and take a limit, then we have 1/2, right? I feel some kind of an irritation looking at that. You have a sequence of points. Each point, oh, I don't understand why it doesn't work. Sometimes, who can consult me how to manage this microphone? So each point has dimension 0, yes, and we have countable union of sets. What? Not always. Sometimes it works, sometimes it doesn't. Okay, so if it stops, you see, sometimes it stops working. Yes. So we have countable set of points. Each point has dimension 0. Each finite number of points have dimension 0, but the whole sequence has dimension 1/2. So this dimension is bad. Why it is bad? Because if we pass to a limit, it jumps. Yes. If you take a countable union, if we have some dimension, then we need to have such formula: dimension of union of an equals to the supremum of dimension of an. So good mathematical dimension needs to obey this law, and box dimension doesn't obey this law, so it is not very good, but it is convenient. We put a set in a box and just count boxes and have dimension in our heads. Therefore, I need to understand the notion of dimension. So, initially there were only integer dimension. A line had dimension 1, a plane had dimension 2, space had dimension 3, etc. Yes? But then there was a theory of integration. Then theory of integration was developed for lines, plane, space, and then Konstantin Karateodori understood how to use Lebesgue integration, how to organize Lebesgue integration on surfaces and curves, on subsets of surfaces and curves. And so he introduced the Karateodori measure, yes, and this gave an impulse to Felix Hausdorff to extend this measure to different dimensions. This happened in 1918, yes, and at that moment Felix Hausdorff was in Greifswald, where Christoph Bond lives all his life. Yes, okay. So, Hausdorff dimension was invented by Hausdorff in Greifswald in 1918. And now I will explain you what is the Hausdorff measure and Hausdorff dimension. Because the box dimension is just a very simplified version of Hausdorff dimension. Yes. So first we had the Hausdorff dimension, and then consider a very complicated curve. Consider a curve. How to measure its length? It's very simple. We take and cover this curve with balls and sum up the diameters of balls. Yes? And this sum of diameters of balls gives us some kind of approximation of the length of the line. But this is not very good, because if curve looks this way, if balls are large, then the length of the curve may be 100 times greater than the diameter of this ball. Therefore, we need, from first point of view, we need to minimize the sum of diameters of balls. And second, we need to, at the same time, we need to minimize let the diameters tend to 0. Oh, you need to change the batteries. Okay. So what we do? So let this be curve. Let me denote it by gamma. So length of gamma is a limit as epsilon tends to 0 of infimum of the sum of diameters of balls such that diameter of balls is less than 0 and union of balls contain gamma. Okay? So we consider families of balls of diameter less than 0, yes, which cover gamma, yes. And among all these coverings, we will take the lower bound of such sum for these coverings, and after that we begin to diminish epsilon, yes. So if epsilon becomes smaller, this family becomes more poor. Yes? Therefore, this lower bound will rise. So this will be the upper limit of this lower bounds, but since it's monotonous, it's just limit. And it will give us the length of gamma. Very good. If gamma is a curve, so we get this length. Sometimes the length of curve may be infinity. When we have sine of 1 divided by x, then we'll get a curve of infinite length. And suppose we have a surface, some very complicated surface in Rn. Yes? Then we take balls which cover this surface, and instead of taking sums of their diameters, we take sums of the squares of these diameters. Multiplied by maybe, so S is P d squared by 4 divided by 4, right? Yes. So we multiplied it by some coefficient, and we get this way, we get the area. So this was what Karateodori understood. And Hausdorff began to think why this number should be an integer. This number may be any number, any positive number. Yes. And therefore, he defined two values. Oh, I need to, so he defined epsilon alpha dimensional Hausdorff content of K as a lower bound of sums of diameters of the sets Ui covering K. Yes, so I will write it K belongs to union Ui, right? And diameter Ui is less than epsilon. So we take some epsilon more than 0, yes? And we consider the sets which have diameter less or equal than epsilon. Yes, maybe less or equal than epsilon. And among all these epsilon covers, we take a lower bound of this value. When epsilon becomes smaller, this number would grow. Yes, because we take a lower bound of some smaller family of coverings, because each epsilon divided by 2 covering is also an epsilon covering, but not all the epsilon covering are epsilon divided by 2 coverings, for example. So, and we take h alpha of k, it will be the limit as epsilon tends to 0 of h alpha epsilon of k. And it is called the alpha dimensional Hausdorff measure of k. How wonderful it is. So we can consider different dimensions, and in different dimensions we can take measures. But the situation is not so peaceful as this can look from the first sight. Suppose epsilon alpha dimensional measure of k is finite. Suppose we took some set k, it may be fractal, it may be anything, yes, and its measure is some number which is less than plus infinity. Take beta more than alpha, and let us count h beta of k. H beta of k. Oh yes, h beta. So if we take h beta epsilon of k, it will be the lower bound of all sums of ui to the power of beta, and diameter of ui is less than epsilon, right? I don't write that they cover k. It is supposed by default, yes. And we can write it. It will be less or equal. So you see, ui to the power of beta is ui to the power of beta minus alpha multiplied by ui to the power of alpha, right? And this is less than epsilon to the power of beta minus alpha multiplied by ui to the power of alpha. Sorry. Do you see what I write? You see? Okay. Then it will be less than epsilon to the power of beta minus alpha, right? Multiplied by infimum of sum of ui to the power of alpha, right? This value tends to some number m as epsilon tends to 0. But this value tends, well, to 0 because beta minus alpha is more than 0. Therefore, this value tends to 0. if alpha dimensional measure is finite, then on next stage it becomes 0. So we have a very nice picture how it looks like. We can draw a graph. You can see this graph in Falconer's book. So we have this value will be infinity, this value will be 0, and we take some alpha. And so if h alpha of k is finite, then for all greater beta, the beta dimensional measure of k is 0. From the, if we look at this medal from the other side, if h alpha of k is not 0, then for beta less than alpha, it must be infinite. Yes. And there is only one value which is on the border between infinity and 0. Yes. So this alpha is called Hausdorff dimension of the set K. Alpha is Hausdorff dimension of the set K. This is the definition of Hausdorff dimension. You see, it's very good. This picture. Yes. If h alpha of k is finite, then for beta more than alpha, h beta of k is 0, right? We proved it. From the other side, if h alpha of beta is more than 0, then h beta of k is infinity. Yes, because if it is not infinity, then h alpha of k is 0. So there is only one value which is the border between infinite value of measure and 0 values of measure. And this value may be 0, may be non-zero, and may be infinite, depending on the case. So we can produce sets whose Hausdorff dimension, for example, is 1, and one-dimensional measure is 0. It is possible. We can create sets of whose Hausdorff dimension is 1, and one-dimensional measure is infinite. Yes? So can we make a set which has Hausdorff dimension, which has a Hausdorff dimension 1 and whose measure is 0? Let us, I will draw, I will create an example of such set. This example will need some further questions, knowing of some further questions, which I will explain later. For example, Suppose we have a counter set with a ratio Q. Q counter set. K is QK union 1 minus Q 0 multiplied by QK, right? So IK QK, this is QK, and this is 1 minus Q, it will be QK2, right? So it will create a counter set. Yes. This counter set has dimension logarithm of 2 logarithm of 2 divided by logarithm 1 divided by Q. Yes? Therefore, we can create counter sets of arbitrary dimension. And then we make sequence Qn which tends to 1/2, yes? Which grows to 1/2, yes? And then we make the following procedure. First, we have here a counter set with coefficient Q1. Then we take a counter set with coefficient Q2. Then we take a counter set with coefficient Q3, etc., right? So this the dimension of this set will be logarithm 2 divided by logarithm 1 divided by Q1, right? If we take some union up to nth copy, this dimension will be logarithm 2 divided by logarithm 1 divided by Qn, right? On n step. If n tends to 0, then dimension tends to 1. Each of these set has 0 one-dimensional measure, yes? The countable union of sets of measure 0 is a set of measure 0, right? Therefore, we have the set whose dimension is 1, but measure is 0. So it is very simple example. It can be created also by other means, but so what is our timetable when we need to? Oh, yes, we have half an hour. Okay, that's good. That's good. I need to remind you some properties of Hausdorff alpha dimensional Hausdorff measure. So first, the properties are properties of H alpha. Yes. Which we need. First, the Hausdorff measure for each alpha, the Hausdorff measure of empty set is 0. It's obvious. Because we can cover by set of arbitrary small diameter. Yes. Then, if A is contained in B, then alpha dimension measure of A is lesser or equal than alpha dimension measure of B, right? Then alpha dimension measure of union of the sets AJ, a countable union, is less or equal than the sum of measure H alpha of AJ. Yes. And for any, usually when we consider measure, we consider so-called Borel measures for which all Borel sets are measurable. But for us it's sufficient to know that if we have a Borel measure, then open sets and closed sets are measurable, and all other just follow by measurability of unions and intersections. Yes. So for any compact, because non-compact sets compact, or and any open set A or any open set K is H alpha measurable. What does it mean the set is measurable? Consider some set A and set K. Yes? If the measure of A for any A containing K, H alpha of A equals H alpha of A minus K plus H alpha of K. This means that K is measurable. If the set is measurable, and if we cut it from other set, then the measure of the set diminished just by the measure of this K. If the set is not measurable, for example, I consider some non-measurable set. Yes? Then it has upper and lower measure. If we erase, then we erase lower measure, and the sum of the measure of this set and this difference will be greater than the measure of A. Okay. So all compact set, all open set, all closed set are measurable with respect to Hausdorff alpha measure. So the Hausdorff dimension is the border between those alpha of which H alpha of K is 0 and those alpha for which H alpha of K is infinity. But you see, how to how to determine which set has finite Hausdorff measure and infinite Hausdorff measure, because Hausdorff measure is not easy to compute, you see? Because we consider epsilon content and then pass to limit, where as epsilon goes to 0, we get this limit, and this limit, so I suppose it's not easy to make calculations to find this border, yes? But this question is simplified in some way. How it is simplified? Denote by h alpha infinity of k and the number which is equal to the following thing. It will be lower limit or lower bound of some ui to the power of beta, or sorry, alpha, so we erase the restriction on diameters. And we get the thing which is called Hausdorff content of K. This value is more easy to find, yes? We just consider different covers and find the optimal cover. Yes, no matter how large or small the sets are, yes? Not very convenient to find, but much more simple than to find Hausdorff measure. So, whereas there is the following theorem. H alpha of k is 0 if and of only if H alpha infinity of k is 0. You see? If set has 0 alpha dimension Hausdorff measure, then it has 0 alpha dimension Hausdorff content. Let us compare two definitions. Yes. First I need to notice that H alpha of k is greater or equal than H alpha infinity of k. So if this is 0, then this is also 0. because both values are non-negative. We have no negative measures. Yes? Right. So, this implication is automatical. No. This implication is automatical, right? If this is 0, then this is 0 too. Now suppose I have a feeling that you are tired, a little. But I have no anecdote in my mind at that moment. At that moment, good lecturer pronounces some kind of joke, and this monotonicity of writing and all this thing is erased, and so, but we have just 5 minutes left, or maybe a little more. Yes. So suppose h alpha infinity of k is 0. Yes. So suppose it is 0. Then what happens? For any then for any delta more than 0, there is a family En of sets such that sum of diameters of diameters of En to the power of alpha less than delta, right? For any delta, we have a cover of k for which the sum of the diameters to the power of alpha is less than delta. This gives us 0 in the limit, yes? If we look at this sum, then we see that diameter of each, I cannot write E, I write sigma. For any n, diameter of En less than, right? All these values are positive, then each value is less than, each of these values is less than delta, then En, diameter of En, less than the root of delta with the power alpha. Yes? So, if epsilon is if delta is epsilon to the power of alpha, yes, then h alpha epsilon of k is less than epsilon to the power of alpha, right? Yes. Also less than delta. Yes. Therefore, so less than epsilon to the power of alpha, yes? Yes. If we tend epsilon to 0, we get that h alpha epsilon, h alpha of E equals 0. Oh, k, sorry. I have E in my scratches, therefore, but then so these two equalities are equivalent. Yes, So we can, when we suppose to find Hausdorff dimension, we just look at alpha dimensional Hausdorff content and give us the evaluation of Hausdorff dimension. So maybe at that moment we need to stop our lecture and have sufficient break to refresh our brains. If you have any question, please. So we discussed a lot. We have a lot of new notions. I need they can be packed optimally somehow in your brains. So after the break, we'll remind all this story in short. Can you tell me what is the one-dimensional Hausdorff content of unit interval? Content of unit interval. How do you think? Please count one-dimensional Hausdorff content of unit interval. One, right. Okay. And what is the one-dimensional Hausdorff content of the Cantor set? 0, okay. And what is one-dimensional Hausdorff content of a square? Unit square. Infinity, yes, okay. You see, you compute alpha dimensional Hausdorff content of different sets very easily. So my congratulations to you. Okay, so you can relax. If you have questions, you can come closer and ask me. If you have no questions, you can feel free to stand up and walk into the corridor. You are not, there are no restrictions. the content of previous lecture. Just for reference, I remind what was on the previous lecture. So first thing what we discussed not all the previous lecture, but the part which is concerned with dimension. Yes. So first we defined box dimension. Do you remember what is box dimension? Have you heard about the box dimension? Yes. Yes, you're you're laughing, it means that you heard. Yes. So it is, there is upper box dimension and lower box dimension, but we will define the case when it exists. So upper and lower are the same, and therefore the box dimension is equal to or fractal dimension, whatever you like to. It's of k. Its limit as epsilon tends to 0, and here is logarithm of number of boxes. Epsilon boxes covering epsilon k divided by a logarithm of 1 divided by epsilon, or minus logarithm epsilon, but I don't like minus in the denominator, so yes. So nk epsilon may be a number of boxes sets of diameter epsilon, or balls or non-intersecting balls with centers in K. Yes. Second, we proved that box dimension of finite set is equal to what? 0. That was very good. And I skip counter set and 0, 1, and but box dimension of a sequence 1, 1/2, 1/3, 1/nth, and finally 0. Yes, a box dimension of this sequence will be 1 divided by 2. The question is, and if I have a sequence 1 divided by n squared, what will be its box dimension? So the question arises, I have a sequence 1, 1/4, 1/9, 1/16. It's a 1 divided by n squared. Yes? And I add here 0, of course. Can you compute its box dimension? Can you evaluate its box dimension? So we again have this sequence. 1, 1, 1/4, 1 divided by n squared, 1 divided by n plus 1 squared, etc. 0. How to find some minimal covering? Yes, but by intervals of equal length. So suppose we have 1 divided by, I don't know if 1 divided by n cube is optimal, but it will be n intervals of this size, yes? And here we have also, yes, okay, this part, yes. And here we have n minus 1. Of intervals of that size. Yes? So, n of k epsilon is equal to 2n minus 1 again, but logarithm of 1 divided by epsilon is equal to 1 divided by epsilon is n cube. Yes? So you see a logarithm nk epsilon divided by logarithm n cube. So 1/3. If you pass to a limit as n tends to infinity, it will be 1/3. Yes. And I suppose that this is a minimal number of such intervals, right? Of course, we can consider some other number, maybe 1 divided by n to the power of 4, but so difference between these two elements will be less than 1 divided by n divided to the, oh no, it will be greater. No, it is not good. Yes. So we have n squared multiplied by 1 divided by n to the power of 4. Here we have n minus 1, and you have n squared plus n minus 1 logarithm divided by a logarithm of n, 4 logarithm of n. It will be 1/2. So there is a problem which is the optimal size. Yes, because we need to minimize this number. But here we have most probably there will be some gaps. So n cube is better. N cube is better. Okay. So in general, there is a question. I cannot give you an exact answer because I need some time to think. And if you have a sequence 1 divided by n to the power of alpha, and what will be the dimension of this sequence? And we will discuss it later. Okay. So now, next moment which we worked with, we defined box dimension and proved it, shown this example. Yes, which shows that box dimension is bad because it is not stable under countable unions. Countable unions of sets having box dimension 1, 0 have dimension 1 divided by 2. Then we defined Hausdorff dimension. Dimension. What we have done, we defined H alpha of k H alpha. First we defined H alpha epsilon of k. It was the lower bound of the sums sigma ui to the power of alpha, where ui is an epsilon cover of k. Yes. First we epsilon Hausdorff content of dimension alpha we defined, and then we pass to a limit as epsilon tends to 0. This limit will give us alpha dimensional Hausdorff measure of k. Okay. So this was our third step. And then we proved that if A lies in B, then H alpha of A is less than H alpha of B. Yes. And H alpha of union of AK equals this, or lesser equal, is lesser or equal than the sum of H alpha of AK. And what was the most striking, that if H alpha of K is less than infinity, and if beta is more than alpha, then H beta of K is 0. Is 0. Yes. Therefore, we obtained the following graph. We have alpha, there is unique alpha, which is the boundary between infinite values of Hausdorff alpha dimensional measures and 0 values. Yes, here we have infinity, here we have 0, and alpha is called the Hausdorff dimension of K. So in that area, h beta of K is infinity. In this area, h beta of K is 0. And there is only one value which splits these two intervals. Yes. Then we proved that if h alpha of k is 0, if and only if h alpha infinity of k is 0. H alpha infinity is the Hausdorff content. H alpha infinity of k is the lower bound of some ui to the power of alpha, where ui is a cover. So it's lower bound over all covers of K. So instead of finding h beta of K, which is not easy to find, we just compute h beta infinity of K, which is more simple. And this was the end of previous lecture, right? Do you have any questions concerning this material? Yes? Is everything okay? So let us continue. So our problem is to evaluate the Hausdorff dimension of K. So I will change the order, which I planned one order, but I will change it a little, and it will have some reasons. So suppose K is a self-similar set. Let K be the union of Si of K, where I changed from 1 to m. Then and let Q will be maximal coefficient, maximal contraction ratio of Si. Then we can represent K if you have a multi-index I1, I2, In, then Si1, In of K, or Ki1, In, right? I1. If you have a copy with the address I1, IN, then this copy has the diameter less than q to the power of n multiplied by the diameter of k. Right? So these copies form a cover of K. Yes? These copies form Qn cover of K. You see? Therefore, if Q1 to the power of alpha plus Qm to the power of alpha less than 1, then the sum Ki1 In diameters of Ki1 In to the power of alpha or let us denote this sum by some maybe P alpha, yes, which is less than 1, right? This sum is equal to sum of Ki Ki to the power of so it will be less than Q to the power of n, Q to the power of n, diameter of K to the power of no, sorry. I began too fast and then so K is union of K1 union Km, right? And it is at the same K11 union K12 union Kmm. So this will be, if you consider the contraction ratios, then here we will contraction ratio Q1, here we have Qm, yes? So the sum of these diameters will be less than Q1 plus Qm, multiplied by the diameter of K, yes? And if you have K11, K12, Kmn, it will be, the sum of these diameters will be Q1 plus Qm to the power of 2 multiplied by diameter of K, right? Do you understand? Yes. Because Q1 okay, this also so I have some problems with taking sums. So taking sums, yes. Therefore, the sum of ki to the power of alpha if we have ki to the power of alpha and the sum of kij to the power of alpha is equal the sum of ki to the power of alpha squared, right? Yes or no? Okay, so for example, K1 plus K2, K1 alpha plus K2 alpha plus K3 alpha, you consider that. And if you have K11 alpha plus K12 alpha plus K, I don't write modules, let be K13 alpha plus K21 alpha plus K33 alpha, it will be K1 plus K2 plus K3 is squared. Yes, so it's just a property of binomial coefficients. Yes. Okay, then therefore the sum of ki1 in to the power of alpha is less than q1 alpha plus qm to the power of alpha to the power of n multiplied by diameter of k to the power of alpha. Is that right? You see, ki1 in to the power of alpha is k to the power qi1 i1 i2 in to the power of alpha multiplied by k to the power of alpha, right? Is that so? If you have a diameter of k, diameter of ki1 in is diameter of k multiplied by this coefficient. So if we take alpha's power, we have the same. Then if you have the sum of ki1 in to the power of alpha, then you transform it to this sum, yes? It will be transformed to the sum of this, and alpha is taken out this, but the sum of qi1 in to the power of sum of to the power of alpha is the same as q1 plus qm to the power of alpha. Okay. So if the sets ki1 in form form a q to the power of n multiplied by diameter k cover of k. Okay. So if q to the power of n multiplied by k is less than epsilon, then it's an epsilon cover. Yes? Yes. Then it's an epsilon cover. It's an epsilon cover of k, where of k, and the sum of diameters of this cover is less than q1 plus qm to the power of a multiplied by k to the power of alpha, right? Therefore, h epsilon alpha of k will be is less than p to the power of n. Where is? Oh, yes. If this sum is denoted by p, it will be less than p to the power of n multiplied by k to the power of alpha. If epsilon tends to 0, then n tends to infinity, right? And it implies that h alpha of k is 0. You see, if this sum is less than 1, is the sum q1 plus q2 plus qm to the power of alpha is less than 1, then alpha dimensional measure of k is 0. And the first chance when this measure is not 0 is when q1 plus qm to the power of alpha equals 1. Right? Okay. So did you write down all these things? Can I erase and write next? If q1 to the power of s plus q2 to the power of s plus qm to the power of s equals 1, then for any epsilon, so, or maybe for any n, the sum of k I1, I2, In to the power of s is equal to k to the power of s. Because q1, the sum of q I1, I2, In to the power of s is equal to q1 1s plus qm to the power of s to the power of n, right? And this is 1. Therefore, we have such equation. It means that hs of k is hs of k is finite. Therefore, Hausdorff dimension of k is less or equal than s. Now I repeat again. So we have a self-similar sets, and the sum of q1 to the power of s plus qm to the power of s is, if it is equal to 1, then Hausdorff dimension of this set is less or equal than s. So it was 1944 when this was discovered by Patrick Moran. Patrick Moran was an Australian mathematician, and in Canberra, in the University of Canberra, there's special Moran's Memorial Building. And therefore, he considered the self-similar set on the interval, but of course there was no definition of self-similar set, but sets similar to counter set formed by different intervals, and found that they have the dimension of these intervals is satisfied. So if the lengths of these intervals are q1, qm, then dimension of this set k equals, so intervals should be disjoint, then dimension of the set k equals the number s, which is the solution of this equation, which is called Moran's equation. And this S is called the similarity dimension of the system S. S is the similarity dimension of the system S. So by some very happy coincidence, for good self-similar set, the Hausdorff dimension is the same as similarity dimension, and we will try to prove it just now. So now I add this to the list. A similarity dimension is the solution of the equation q1 to the power of s plus qm to the power of s equals 1. Yes. And in the case when we have counter sets, the dimension of this counter-like sets is equal to S. But for any self-similar set, we have that its Hausdorff dimension is less or equal than S, but we need to prove we have an upper bound for Hausdorff dimension of K but we need to give some lower bound. And lower bound is more complicated. To get a lower bound for the Hausdorff dimension of a set, we use so-called mass distribution principle. Suppose let X be a space, and let mu be a positive Borel measure on X. On X such that mu of X is not infinity. So suppose we have some positive finite Borel measure on the space X. Okay. Let mu satisfy the condition for any ball B of XR. So we have a ball of radius R with this center X. Mu of B of XR is less than C multiplied by R to the power of alpha. So suppose this measure is good because the measure of each ball in X is less than constant multiplied by a radius of this ball to the power of alpha. So it's good. All balls are conduct in a similar way. Then our alpha dimensional Hausdorff measure of X is more than equal than its alpha dimensional Hausdorff content, and it is more or equal than mu of X divided by C. Therefore, Hausdorff measure of X is more or equal than alpha. So if all balls are good, yes, then dimension is greater than alpha. How to make it? How consider let B1, Bn, etc. be a cover of X. Of X. Then the sum of measures of Bk is less of or equal than sum of mu, or then sum of then C multiplied by sum of Rk to the power of alpha. Yes? Yes, and it is less than mu of the whole X. Am I right or not? Sorry, 1 second. So, sorry. 1 second. Oh, excuse me, please. Excuse me, please. I wrote wrong things. Mu of X is less than sum of mu of Bk, and this is this way. Yes. Therefore, the sum of Rk to the power of alpha is more or equal than mu of X divided by C. So, sorry, H alpha of X H alpha of yes. 1 second. So maybe I need to write this. Look at this. H alpha of x is more or equal than H alpha infinity of x, and H alpha infinity of x is H alpha infinity of x is the lower bound of sums of ui to the power of alpha, yes, by all covering. Therefore, it is what? I don't hear what you say.
We have one cover right now, given vector extra bn, which covers x, and we got this condition, right? Summation.
Yes, yes, yes.
Alpha. So that is one cover, which will cover x. So infimum of that will also be bounded below by mod.
Oh, yes, 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 yes. You're right. Yeah, you're right. Yes. So this. Oh, yes. So this is just what we have. Yes. Okay. So and so if H alpha of x is so I forgot. Alpha is the if H alpha of x is 0, then if H alpha of x infinity is 0, then Hausdorff dimension of x is less or equal than alpha. Then alpha is greater than. So very sorry, if H alpha infinity of x is more than 0, then alpha is, then Hausdorff dimension of x is greater than alpha, right? Right, yes, this way. Okay. If H alpha of x is more than 0, right? Then dimension of x is greater than alpha, right? So if H alpha of x is in this area, then Hausdorff dimension is greater than alpha. Okay. I just mix right and left, therefore not easy. Okay. So therefore this mass distribution principle gives us a lower bound for the Hausdorff dimension of x. Yes. If we find some mass distribution on X or on K, then we can, using this mass distribution, we can evaluate the Hausdorff dimension of X from below. Yes. Yes. So now we need to prove, to study this one more important question in evaluation of Hausdorff dimension of a self-similar set, and this question is open set condition. What does it mean? Oh. Open set condition. Let K be a self-similar set. So the system S consists of elements S1, Sm of M mappings. We say that the system S satisfies the open set condition if there is an open set O such that first union of Si of O lies in O. So we have an open set and we have its images lie in O. But they not only lie in O, but they also do not intersect. Second condition is for any I not equal to J, Si of O intersection Sj of O is empty. This is very important condition which is sometimes not easy to check, but if it is satisfied, then if a self-similar set satisfies the open set condition, then its Hausdorff dimension, its similarity dimension, and its box dimension are the same. So how to check? For example, how do you think counter set? Does the counter set satisfy the open set condition? What kind of open set you can use for counter set? We just use this interval 0, 1, yes? Its images lie inside 0, 1 and do not intersect. if you have a Sierpinski gasket, what kind of the open set you can use? Of course, you can use the interior of this triangle because its images do not intersect. But even if you take such a hexagon, yes, if you take such a hexagon, it will also be good for checking the open set condition, right? Because the images of this hexagon do not, they have common boundary in some places, but they do not intersect. Yes. But for example, if you take 1 second, I will, no. You know what I will say? 1 second. I will show you one. Yes. Okay, I will discard my changes. If I take twin dragon, yes, do you see it? Then it has very complicated boundary, yes, and the open set for this twin dragon will be twin dragon itself. Yes. So to check, it's not easy to check open set condition because we need to find it. But it is unique, and it is, to construct it is just to construct the attractor. And this is quite simple case, because for Levy curve, the open set will be the interior of this Levy curve, which is not very easy to detect. You see that it is even not easy to see that it exists. Yes. Oh. Oh yes, when in the second part of the day I cannot observe the time. So please. If you have macOS, there is some problem, but you can use text edit, and then erase RTF, because and create a text file. Yes. So create a text file, and it will be call this text file test.aifs. This will be a text file. Then you need to let me look at my manual. What we need to do second and first. Because so you need to write the head of the block, of the first block in this file, and you can write cat code, maybe G. This is just the head of the block, but if you wish to write some other name, you can write anything. Okay. If you like anything, then you can write anything. Okay. Second, first we need to make some experiments with dimension 2, right? So, you write $ dimension equal to, because the action of the program in the case dimension 3 is totally different. And you can also give a name. Give a name, some name. You can write any name you wish. It must begin with some letter. It cannot begin with a number. Yes, but and after that you can make the program. So what will be the first program? For example, you can write this way: K equals 0.5, 0, 1, union 1, 0. This is union. This is union of sets, union of operators, so union of all these actors which we use are multiplied by K. Okay, the program is ready. You have to save this program and check it. But do you have IFS style installed? Yes, yes. Who has no IFS style, this program will not work. Please, can you share with me your happiness? You have a lot of these things enough on YouTube, right? So then you need Oh, it's just the thing which I wanted to see. Yes, okay, you have the interval, right? It's too large. You can diminish it, yes. Oh. Unfortunately, I have now this program here, which you composed because your program is... So if you want to make it smaller, you just press this minus sign. You see? If you need to make it larger, you press this fit to the screen sign. Okay? If you need to make it even larger, you can just make how it is called, make a selection, make a rectangular selection, and it will be enlarged to the... Of course, it is not interesting to enjoy the view of a unit interval. Yes, therefore, we can add something here. Okay, what you wish. For example, if you add 0, 1, you will have... Do you understand what you will have? Add 0, 1, please. Of course, it should be multiplied by k. By k. Yes, we have Sierpinski triangle. Oh. This is very interesting triangle. Did you read that if you have this Sierpinski triangle, rectangular, then for every vertical section, the dimension of this section almost everywhere is equal to 1/2. Who read this? Do you know this now? There is very nice book of Bishop and Paris, and in this book this fact is explained in the first chapter. It's quite... Bishop, Paris. Very good book, because it considers measures, probabilities, and all other things. Okay, so you made this. So I don't like this one, and suppose I will add one more thing. I want to draw some interval. For example, I will be equal to 0.5 star 1, and there will be 1, 1 multiplied by I. This will be an interval. You know what it is. It will be a diagonal, yes? Diagonal in a square. So, is it easy for you to make it? Yes? And now we'll make an experiment. Yes. I will do the following thing. So I will add to this k. So did you get this interval? You cannot understand where to find I? Yes. So when you press this button, you see this button, it will be the list of objects. And when you press this button, you will see the list of objects in the current block. 1 second, I will open some test program. Escape. Excuse me 1 minute. I need to recent. Yes. What was? For example, I will take this program for kids. Yes. So if I open this program, there are 3 blocks with 3 names. Oh, okay. And for example, this is von Koch curve. Yes. So you see, you can also build von Koch curve. You don't need these comments. Since we use rotation and we need to know what pi is, you define pi. You define pi, right? Yes. And also you need to define unit interval, and I will translate this comment. Comments. Dimension, and unit interval. Okay. Do you need some comments to this program? So first we define what pi is, then we make a standard definition of unit interval. Not very compact because we have translation. Then you have union of 2 translations. And this interval A is not shown in the program. This sign shows that it need not to be added to the demonstration. Yes. And then we have a definition of von Koch curve this way. This is not the best way, but sorry. So in this, so your question was how to see the objects. In this program we define 5 objects: K1, K2, K3, K4, and K, right? So let us consider how they do look like. So when you press this button, you see this one, yes? When you press it first time, you have a list of objects, and you can look at them. So K1 is shown on this. I mean, I think it's better to K1 is S. Oh no, K1 is first iteration, right? Yes. And if you have K2, K2 is the second iteration, right? And K3 is third iteration, K4 is fourth iteration, and K is the whole tractor. And now please look here what it is. So you have the Hutchinson operator of the system, right? Then you have the unit interval A, yes? And then if you apply Hutchinson operator S, this one, yes? If you apply S to A, then you will get K1. I will show you K1 again. Sorry, I need some feedback. What you wish. Please tell me what you wish. Or you just need to see this program. You have no questions? You need any help? Yeah. What?
Construct different fractals.
Yes, I understand. If this is understood, I can go further. Yes. So you got the answers to your questions? Yes. Okay. So, you know how to find an object. You know how to hide an object. To hide an object is very simple. You just write this sign and objects becomes hidden in the program. So in this program we construct unit interval, yes, then we get this Hutchinson operator, yes, it's S minus Pinatri 113 1 0 S 1 rotation. So I will never write it in this way. It was constructed by some other persons. I prefer to write more clearly without any one. I don't see where is the multiplication by 1/3. Yes, okay. It was a paradox for me because 1/3 is written in the very end. So first we shrink it 3 times and then apply intervals Usually I write it in different way. If you allow me, I will rewrite it more economically. Okay. So it will be done this. So I will write it in. It will be SS, the other operator. So it will be 1/3 multiplied by, and then I open the bracket, and here we have union of 1 union 2 0 2 0 0. Yes. So if I close this parenthesis, then I will get Hutchison operator of von Koch of counter set. Yes. 1 and 2 0. Yes. Multiplied by 1/3. It will be counter set. You understand? Yes. Then I add. 1 0 0 multiplied by rotation by pi divided by 3. I will just copy it and paste. Oh no, it doesn't paste. It doesn't copy. Rotation by pi divided by... Oh, you have a problem. We need to define the rotation. This rotation. It must be defined in separate block, or it can be defined just here. It's better to define in it's better to define it in separate place. Yes. And also I will write here 3 divided by 2 and 1 2 3 1 2 3 4. This is 3 divided by 2, and this will be square root of 3 divided by 2, right? 0 1 2 3. Therefore I write square root of 3 to the power, 3 to the power 0.5. Yes, 0 is not needed, divided by 2. Okay. Yes. And multiplied by rotation at the angle minus pi divided by 3. Almost the same, but less number of fractions. Okay, this will be close to 1 2 3 4. Okay. So how to let us look at this source file. Yes, in some external editor. So it is what is the name of this files? Let me check. Sorry. For kids, yes, for kids. It was for kids. It was for kids. Oh, it's not easy. For kids. I cannot find it for kids. For name contains four. I'm very unhappy because I cannot find anything. When I see it. I see it for kids IFS. Open with. Excuse me, I will switch off this screen and open this file in my laptop when I see it, and after that I will return back. It is not very convenient because J. Okay. Is it visible? The whole program is the following. So we have I don't know what to do with this. Let me check if it can be magnified. Help, view. So you need to inside your file you need to add a block, one block. So it will be cat code rot. It means rotation, and you need to write that it is hidden, but it is not necessary. You can show it. If you show it, it will be better for you. Yes? Okay. Then, after that, you write Ka equals 0. Ka equals 0. And you write return, and it will be cosine Ka cosine Ka minus sine Ka minus sine Ka sine Ka and cosine Ka. It's a matrix of rotation. So if you have this block in your file, yes? If you have this block in your file, it is used, and when you write rotation, for example, rotation pi divided by 2, you will get a rotation by an angle pi divided by 2. Yes. Okay. So I can make these experiments So if you have these 4 kids, oh no, sorry. I said 1 second, and I need to open it. View. File reload. Okay. File open. Open. Yes, I open it. Yes, okay. Let me check if it is visible. Oh, now it is visible. Yes, you see, it is visible in my program. Okay. So when I edited it and deleted attribute hidden, it is visible in the source, and I will show you where it is placed. In the header. Oh, yeah. View here. So you had this program, then you have this one, and then you let me go to this file. Yes. So I will switch to this block. Yes. It has not my reduction because it was deleted. I forgot this file. Yes, but I see all the blocks now here. No hidden blocks at all. Okay. So when you make a program and you need to use some let us return to your program test IFS. Test AIFS. FS. So you begin with this one. There was the name of main block. Oh no, test IFS. Sorry. I need to look at it once more. So in the very beginning you write, if you open this program, in the very beginning of this program you defines the necessary sub-programs. First will be rotation. Yes. I will keep it open so I don't write this one. Yes. And I write return cosinus cosine Ka minus sine Ka sine Ka and cosine Ka. Then I begin with some other block. So it will be block J. I define the dimension. Dimension equals to, yes, equals to, and write the name, and this will be block J, and I write this, write the name of this block, and it will be test program, for example, and I make an experiment. I have this 0.5 multiplied by, so I just add these strings, yes, 0.5 1 1 1 1 1 multiplied by I. So it will be the diagonal interval, right? And after that, I suppose to make some experiments. 1 0, it will be 0 1 1 multiplied by K. So you have this and that. Yes, if you have, then we can proceed. Add here the interval I. You see? What will happen? What will happen if you add the interval to this operator? Did you make it? So you will, oh, where is this interval added? Yes. I didn't see it. Ah, yes. You see? You see the result, okay? Just add this interval to K. So you have K. You have K equals, I will write it in greater letters. Where is the duster? For example, I write I equals 0.5 multiplied by union of identity and 1 1, right? 1 1 multiplied by I. multiplied by I, right? And then I write K equals, what was it? K, 0.5. And then we have 1, union 1, 0, union 0, 1, and all this multiplied by K. And I added here I. Yes? So you will get this picture. You will have the Sierpinski triangle. Yes? And also you will have this family of images of I. Okay. Okay. So if you have defined some objects, for example, if you have defined this I, if you have defined this I, then we can make different manipulations with them. If you edit to the program rotation in the header of your file, did you add? No? Edit. If you edit, then you can, for example, write B equals I union, for example, this way. 1 rotation by pi divided by 3, and rotation rotation by 2 pi divided by 3, 2 star pi, sorry, pi is this way, pi divided by 3, and apply it to I. Suppose you make this, yes? If you apply this operator, then you will get the family of intervals, right? So, to any of these objects, you can apply different operators and build auxiliary objects.
We were just trying things, just changing numbers, and we were just seeing how the
Алло? Алло? Ты видишь? construct simplest geometrical forms using IFS style. Yes? Polygons. So if you have an IFS style program, you can define unit interval, right? So there are two problems: how to construct a polygon consisting just of lines, yes, and how to construct a shaded polygon, yes. So we'll begin with the first type of polygon. For example, suppose we need to make a hexagon. No, first we need to make a triangle. Let us begin with a triangle, yes? What kind of triangle you wish? You wish to have an equilateral triangle, or you wish to have a triangle with the vertices A, B, C? Whose vertices can be varied. Okay. So we are building a triangle with 3 vertices. Can we make one vertex 0? Yes, one vertex will be fixed. Because if we have 3 vertices, we have 6 variables. Yes? Now we will have 4 ones. So it will be 0, 0, A, B, C, D. Right? So first version is the following. First we build unit interval. Point 0.5 multiplied by 1 union 1, 0, and it will be also multiplied by I. So this operator defines unit interval. When we have a unit interval, we can manipulate it with it. Yes. For example, there are 2 ways of manipulations. We can transform. When we just transform it to an interval with the n0, 0, we can use some affine map or rotation or similarity. Yes? But if we have this one, we need to do something more serious. For that reason, in the header of the program, you need to define one more auxiliary program. It will be used all the time, therefore I need to define it. I will call it SIM, similarity, yes? And it will depend on 4 variables. So you have KA0, KB0, KB0, KC0, and KD0, right? And you need to return the matrix, return the operator, which is a translation to AB, multiplied by a similarity, which, so you have point AB, and you have a point CD, right? So you need to take unit interval, send 0 to AB and 1 to CD. Yes. And what kind of similarity sends this interval to this? First, it will be translation to this. You need to translate the 0 to this point, and then you need to apply a similarity matrix of this form. So C minus A, C minus A, then B minus D, D minus B, C minus A. Okay, so you have this subprogram is defined and it is in your program. Yes? If you have defined this, 1 second, let me make a pause. If you have typed it in your laptop, give me a signal and I will continue. So after the header of the program, you just type these two subprograms, yes? Which will be used all the time. So did you write it?
Sir, I am just trying to do.
Oh, sorry. Oh, no. You made rotation, but you didn't write sim. So, oh, no. Let me, first, you need to add one more string. Yes? You need to write the name of a block. Oh, sorry, shift, cat code, where I am. Here, before A0. And write J, large J, okay. Then, yes, right, dollar dimension is 0, or is 2, yes. Then what we need, L, name, dollar name, dollar. So all the comments, no, this is all?
A is not defined there.
A is 0. I don't know what is A. A is not defined. And what is this?
Can you define it as H?
Oh, no hidden. No hidden. Please.
Remove A?
Yes, remove. You need not. So you define pi. Yes. Find pi. And then you have this. And this is J, right?
Yes, sir.
This is J. Okay. Apply.
Is there saying identifier not found A?
And where is A? Can you?
A sign maybe. Or maybe in this rotation we have used A.
Ah.
I think here we define A.
Yes. Because in the beginning you write KA0. KA equals 0. You see? Do you hear me? You need to define KA and you write here K. Okay. So if you add Ka here, Ka equals 0, K, because it is a variable. Ka equals 0.
So here I have written it, that's why I am writing it.
Да. Не понял. Вот у меня Ka равно нулю. Так? Где? Да. Мне просто K убрать. Вот, да. Да, so Ka was, it was, okay, so если я напишу вот таким образом, то все будет нормально. Ты видишь, да, доску?
Я с запозданием вижу. Секунд по 30 примерно.
Так, то есть можно просто взять А равно нулю, Б равно С. Да, ага. Да, все, ага. So, и здесь тоже я могу А равно, да? Ага. Все. Окей. Ага. So, does it work?
Sir, it automatically erased. I need vanish.
You erase everything, yes.
So I need to type.
Okay, so you define this and this subprogram this way, yes? Really, maybe there is a reason to make these names special names because A, B, C, D may be used somewhere, and to not to mix them with to mix them with internal variables. It's better to make special names for these variables in the subprogram. Ka, yes. Okay. So now when you define this one and this one, yes, when you define this one and this one, so did you succeed in everything? Anything? Let me. Yes, and this case is K. Okay, K. Kc minus Ka. Then it will be okay. No, it is not saved. It is just in the header of the program. You write it in the header of the program. So
now I will type in Notepad, not there.
Yes, it's better to type in Notepad because editing in IFS style is not very convenient. So if you type in Notepad these two programs and after that begin with this triangle, then it will be okay.
Are we still using this software or like so for more in today we use like mostly MATLAB or for writing?
What?
Creating IFS these days we are using this kind of application or the modern one like MATLAB or something?
I don't understand what you mean.
Sir, even today we are using this application or some modern application like MATLAB.
Yes, we have modern application like MATLAB, but they are not designed to build fractals.
They are not?
Yes. Of course, you can use Wolfram Mathematica, but you will have a lot of problems when you will need to solve these problems with fractals. So, okay. So first step is you take node. You open Notepad, yes, and in Notepad you make this file, and in this file you define these two necessary subprograms, right? Necessary subprograms. And after that, when you have these subprograms in the header, then you will make a, and moreover, you define unit interval. Define unit interval, right? Then, when all these things are done, sorry? Yes, this is good. But it is... So I see it, but... Oh, you have this SIM. Yes, you have all these things. Okay, but others do not have. So when you define SIM and rotation, and when you define the interval, then you can build polygons. So do you have this SIM and rotation? Oh, can I look at it? Oh. Yes, I see. Mm-hmm. Is it okay?
Got it. Second polygon is a straight line.
Yes, no, not. But do you have a... Can I see all this file? Yes? Oh, you have SIM, you have rotation.
Yes. And symmetric matrix also, A, B, C, D.
Yes, okay. And then you can build the polygon, yes. And can I look at your work? Yes, okay. Please, if anyone... So please.
Add in the system, but if we use I is equal to 5 star I.
Yes, yeah, and this is unit interval, right? You're absolutely right. This is what I supposed to have. Yes, but where is the whole file? Can I look at this whole file in some text editor, like Notepad? Do you have Notepad? But in Windows you have Notepad or Notepad++. But I have this yes.
Don't try and add in IFSL style.
Yes.
I use
okay.
this one.
Yes, okay. So in this program you can add what you wish, because you have so if you press this button second time, you will see that you have KIBG. You have all this needed. Oh, B, okay. Okay. Who needs assistance?
Do we need to write the subprograms one below the other?
Oh, yes. You can try to add them below, but it's better if you consider all this in some text editor.
Okay.
Can you open?
Like this one?
Oh, yes.
Okay.
And But this is not this file. You need open IFS file in text editor. Yes, open with right. No. Other. And sorry, you have macOS. Yes. In macOS I use gedit. Gedit, yes. Gedit, because of course you can text, how did this, text edit. Yes, okay, open. Oh, but this is not the whole.
You can copy and paste it.
Oh, yes, you can copy and paste here.
But it is showing some.
Because it was not saved, because in initial file is still preserved in its initial form. Because if you typed it in here, yes, you need to save it,
Yes.
and then open it in text editor.
Okay.
Yes. Otherwise, it is just here in this program window, and yes, you can save it under some other name. Okay, this is okay. Okay, sorry. If you have A, B, C, D, then you need to have A, B, C, D here. No, okay, yes. Okay.
Now I have to save it. But here I have used KA.
No.
Is it fine?
Yes, here it is. It is okay. Yes.
Save it?
Yes, but you need to add here some programs. So begin with header J. Yes. Header. Where it is?
Which one?
So you have defined two blocks, and then SIM. You need to use large letter or small. There is two large differences, yes. And then you add this one, where is cat code, maybe G. Okay. You define the dimension, and all other things. Okay. Who needs assistance? No. Oh, so if you don't need the assistance, you can give the assistance to others. Yes. And who else? And what's about you, Vijay? Can you come closer? Yes. This is SIM is so you have Windows, right? Therefore you can use Notepad and open this file in Notepad to see all the programs which are hidden and edit. It's better to use external editor for okay, so this is your file in what? In Notepad, yes, okay. So, okay, but you need to add here some operators. Can you please open this IFS tile once again? Right, and I don't understand. You see the source, but where is the source for this triangle? Did you erase it? Oh, okay. You see, sometimes K is small, sometimes it's a capital letter. Well, unfortunately, the program doesn't understand this change. It doesn't identify capital K with small k. Yes, line and line and block. So you have a rotation. Ka is you see it is large, and here it is sometimes large, sometimes small, right? Right. So you need to use the same k. It doesn't admit capitalization of letters. Yes, yes, of course you need to make it small, yes. Ka is 0, okay. Now it's all okay, then you have SIM, yes, Ka, Kb. Oh no, if you have KABCD, then you need to have KABCD here. Otherwise, you need...
minus D, B minus D, D
yes, just remove K here.
Oh.
In each of the strings. Okay, now it's okay. So this is the program, and this doesn't belong to these two subprograms, right? So let us shift it, put it later, right? And begin a new block. Yes, and define the dimension. Define dimension, and after that you can copy all this. If it copies, yes, just in case, open text editor.
Text editor. What file?
Notepad. Notepad, yes. Notepad is enough. Some very simple text editor. Usually when I use Windows, I use Notepad++, because it is better adapted to programmers. Yes, okay. Who has questions? Who has problems? This is okay. A, K. You see, this all letters are capital, right? K, K, K. Then it's okay. If you begin to change capital to non-capital, it will be a problem. It will be different letters, yes. Okay, so these are two blocks defining subprograms, yes. This is very good. And now you need to save this file. Just save. File, save, this, save. Yes? Oh, they have saved. So, just copy all this. Okay. Copy all this text, copy. If it copies, open it in Notepad. Open Notepad. Create a new file in Notepad. Sorry, you have. Do you have a Notepad editor? But you have Windows. This is Windows. Oh, yes, Windows. In Windows you have Notepad. No? And what text editor you have in Windows? No, sorry. Where is the program? See, I didn't use Windows since 2013, 12 years. So, tell me please, is there Notepad now in Windows? KLM. It's impossible. The time changed. Oh, yes, it is. Okay. What file? Okay. File. Sorry. Opa. Okay. And you need to save this file. Save as test AIFS. Test point AIFS, all right, and okay, save. Now you have test AIFS. After that, you have two blocks here, but it's better to have some space between them, and then you begin the new block. Sorry, why doesn't, okay. You begin, press the cat code, press the name of the block, yes, then begin your work. Oh, you need to press the dimension. Dimension is 2, right? And after that you can begin your work. Do you need any assistance? Hmm? Oh, it's a great success. You have name test, yes. So it's very good. So it is test 51. Oh, 151 is better. Yes. Okay. So you have this all, yes. So we can proceed to work. Everything is ready for work. So you saved it, yes. So you need to change it name. So I told that 151 will be good. So you saved it, yes, and you can open it in. Oh, sorry, test 151 is not. What is the AIFS? Oh, but you need to erase txt. So you need to edit the. I will never excuse you. What happens?
So
this is a notepad, yes. So you need to save this file as an IFS file. Maybe 111.AIFS. And it will be not text document. Okay. Save. Can you check what is the file extension? Oh, it's okay. Open it with IFS style. Huh?
IFS style.
You opened it in IFS style?
Now I have to apply this one.
Oh, yes, okay, apply. Error in block 4. Oh, sorry. I cannot see. G dimension. Maybe you have. And what is this?
Open bracket, I think.
Yes, they don't understand opened and not closed. Apply it again. Again. And what is block 4? Again. 0.5 multiplied 1, 1, 0 multiplied by I, yes. And but what is the block? Let me check it. Check enter. Here every. And what is this?
No, there is union.
K. K and nothing more, right? And K is large or small?
Small.
And first
This one is for large.
large. Yes. So okay. Apply. It some 1, 1, 0, 0, 1. Yes, here, yes. K equals 0.5 star 1 union 1, 0 union 0, 1. How do you think about this parenthesis? Should it be closed before K? No, it should be closed. No, it is open, but it is not closed, right?
Put this bracket over there.
Oh, not bracket. You need to, if you open, where is shift, and where is, and you need to close it. Let us check what happens. Wow. Now it is in 6. Let us check what happens in 6. And what is this point? What does this point means? You see? It is a star. Yes, okay. Please press a star. Yes. And C plus A is impossible. C minus A is here. C minus A, right? Okay. Let us check. Oh. It works. It works. No mistakes. But I don't see what happens. No, source. Sim. Yes. I don't understand. I don't see the whole file. Yes. Oh, yes. It is here.
This is first one.
So this is. Let me check. You have the red sim and the first. Yes, it is here. Okay. So this one. Yes. And this is not G. This will be J1. G1. G1. Because you cannot have different blocks should have different names. So if it is G1, so does it need the things which you used in G? Okay, and say C minus A. Oh, but this will be K large or K small. K. You have different Ks. Okay. So you need to save it. Save. It will be different one. No. Don't change the extension. Okay, save. Save. Okay. And open this file. This is just one. I don't see the name. 11.1113. It's 1113? Oh. Where is 1113? Can you open it with IFS? No. Do you have IFS style?
Running online.
Oh, you're running online. Yes. Can you install it? It takes, I think it takes 20 seconds. Very, very long time. You cannot survive that. So, do you need some help?
I am able to do the equilateral one. I mean
But you, so please tell, are you ready to, did you install these two subprograms? Yes? And you have a working file which contains these subprograms? Yes. So if everyone agrees, then I will go to the next step. How to construct a triangle. You have also this interval, yes, 0, 1. Okay. I will write this way. Triangle is SIM of 0, 0, A, B, union S. We didn't define A, B, C, D. What? You defined? No. We have A, B, C, D here. Yes? For example, you have some A, B, C, D. Let it be 1, 3, for example. Yes? A, B. It will be 1, 3, 1. Yes? Okay, it will be 3, 1. So you have 3, 1. Yes? And let this be, CD will be, for example, 2, 3. Okay. Okay? And you make this union of three operators SIM 0031, 0023, 0023, yes, and SIM 3123, 3123, right? And you have, do you see what I have written? Yes, do you see? Is it visible for everyone? Can you use it? Yes. If, then put them in parentheses and apply to the I. And you will have a triangle. And this will be triangle in which I is oriented this way, 0, 0, 1, this, and this. There will be 3 arrows. No, you won't see these arrows. To make these arrows, we need to construct an arrow. And we will do that, definitely. But you will have a triangle. It's not very great, but nevertheless, it's a victory. Yes. Very small. A great victory is a chain of small victories. Yes. Okay, so now you have this one, and so I draw these arrows. So I will let us introduce how to draw an arrow. So, let us write this way. Arrow is identity union point 0.75 multiplied by I will make very small arrows. 0.07, yes, 0.07, and two rotations. Rotation 3 multiplied by pi divided by 2. No. So I need to have this rotation. And this is 3 multiplied by pi divided by 4. Yes? And add rotation 3 multiplied by 3, 4, 5. 5 multiplied by pi divided by 4. Yes, close this bracket, and all this multiplied by I. Yes. Oh, you can I write it with the magnification? This is not unique way to construct an arrow. So arrow will be it's better to write this way. 1, I have the unit interval, then I take 0.75 translation, yes, and then I apply 0.7 contraction, yes, and I multiply it by 2 rotation by 3 divided by 4 multiplied by pi, and union rotation. Oh, you can make it this way: -3 multiplied by 4 multiplied by 5, -3 divided by 4 multiplied by pi. This is the same, yes? 7 divided, also 5 plus 3 is 2 pi, and then close, and all this applied to the interval I, yes? Okay? You see, this is very simple object, but in your constructions, you need to see not only how the intervals are placed on the plane, but also in what direction they are oriented, yes? Because when it goes from left to right, and when it goes from right to left, these are two different things, yes? So do you see what is written here? If you don't see, you can come closer. What?
After the equality sign, there is a bracket opening, right? So whether it is closing
Oh, please. Oh. Oh. SIM. Open, closed. Huh? ARI. Oh. Oh, no, no, no opening. Yes, yes, yes. I, and then this opening. I don't hear. Can you come and show? I know this is very difficult for you, but what is
when
the?
you wrote it here, the bracket is opening here, but it's not closing anywhere.
Oh, 1, 2, 2, 3, 3, 1.
Here also, right?
Sorry. 1, 2, 3, 3, 4, 4. Yes. Yes, yes. 1 second. Rotation plus rotation must be closed here. Okay. Thank you very much. I tried to write it in very large letters, but I am afraid that you can recognize what is written on the blackboard. Yes. So, if you wish, I can write it again in very large letters. So please give me a sign. If you don't need, then I will stay quiet and don't make any attempts. But if you need that, please. You see, these arrows are auxiliary things, but they are very necessary because they allow us to test errors. Where is my laptop? Where it is? Sorry. I will switch off it for a second. I need to find one file. I will find one file and then after that I will return back the fractal book. No, what's in file? Open recent. Sin. Yes. No, that one. Second, then what is recents? File open recent. No, not that. On the structure of, oh yes. Do you have any questions? No. No network connection is. Sorry. Back home. Apps source.
Sources, HDMI.
Okay.
Now it will connect.
Oh yes. Very complicated. Yes.
No, it's not.
Yes. Let it be so. Let it be this way. Okay, is it okay? Can we continue? So, did you construct an arrow? Yes? So, please do this way. Construct a triangle consisting of arrows. Yes? Excuse me, please. Oh. Which variable? Show me the T. What is T? Yes. Oh. Sim 003. Do you have sim?
Yeah.
Yes, sim. It is here. So, 1 second. Let me check. It works. And show me again the text. So B is shown and T is not shown.
A, B, and I variable is showing there, but T is not showing.
And it doesn't cry about any kind of mistake, no? it is here. Let me check what happens. KBI. What is K? K. What is B? This I is here and T is not here. It's fantastic. Did you apply SIM to something else? No? Maybe it cannot read SIM? No, but if it cannot read SIM, it must say that something is wrong. SIM 0031, 0023, 3123. Where is the definition of SIM? Is it possible to see? A, B, C, D, 0, A, B, multiply 7 minus A, minus A, and Y, and please erase this I, and apply it, okay, and return back to this program, to the test, apply, and look at the list of the objects. Yes, because in this test, I is here, K is here, so
Thank you, sir.
I don't understand how it happened. It's a surprise, great surprise for me. Oh, 3 pi divided by 4 is too much. Yes, these arrows. So you see, when I defined arrows, I had a rotation by 3 pi divided by 4. It's not good. It's not good because they are looks this way. Yes, too wide. Yes, too wide. So it may be 5 pi divided by 6. 3, 5 pi divided by 6. 5 pi divided by 6. It will be better. It will look more harmoniously.
And 3 pi by 6 actually is very,
Wow.
very small angle.
3 pi divided
Actually, it should be 5 pi by 6 and 7 pi by 6, I guess.
5 plus 5 by 6 and minus 5 by 6. Because this
It's 5 pi by 6 and 7 pi by 6. Then it's coming like this.
okay, this is okay. It's okay. 5 and 7 is 5. 7 is minus 5. 7 plus 5 is 12 divided by 6 is 2 pi. So it is the same. 7 pi by 6 and minus 5 by 6 give the same direction. Okay. Oh, but why you made these arrows at the end? Yes, it's better because they will mix together. Yes, yes. So who succeeded in constructing a triangle consisting of arrows? Show me. No, still not. Okay, you have no success.
No, sir. We are not even able to get arrows.
What happens? Arrows. 5 divided by 6 minus 5 divided by 6, it's okay. I 0.75 0 and rotation and rotation. Two rotations are grouped. Yes?
Yes, sir.
And where is this arrow? Which the thing which you called arrow?
No, sir, it's not showing.
There
We
is no.
first tried whether
Oh yes. What's about the rotation?
its rotation is correct
Correct.
because we tried to rotate unit.
Yes. Okay.
Yeah, like
No problem. Yes. I just check everything.
yeah, sure, sir.
No matter how. This
This is
is.
also working.
This
We
is
try
also.
to make triangle.
Yes. So you make me feel guilty for all these things. Yes. 1 second. S1. What is this? SJ.
No,
What?
S is triangle. This is
J is what? What it is? I don't understand what it is.
this curve, this like this.
Okay, this one covers.
This.
Oh yes. Okay, by you made it invisible for.
Yeah. To check whether
It's your decision.
Yeah.
I cannot argue. Pi is okay. S5 is okay.
yeah, S5 is
Okay, and arrow doesn't work.
yeah.
Right? Minus 0.7 multiplied by rotation. Oh yes, very interesting. Rotation pi divided by 6, and there is some strange parenthesis. This, do you see it? The second rotation. So you have a rotation, one rotation and second rotation,
Yeah.
and they are grouped. Let us apply it again. Okay, I don't understand. Can you view where it is file? I forgot it. Maybe here. Yes, user settings, user interface settings. Scale. Make scale larger. Sorry. Oh, it will be better.
Yeah.
Yes. So row I is okay, and then you have 0.75 multiplied by 2 rotation. Let me make rotation and rotation. 2 rotations multiplied by I. It's multiplied by minus and y minus. Let this be plus. I don't know, but I made it plus pi 5 pi. So pi is working. Yes,
Yes,
pi
sir.
is working. Yes. Okay, let us apply it. Oh no, very strange.
Yeah, we have to add one bracket here.
One more bracket. Why? Rotation pi.
Closed.
But what is the reason for this? For this bracket? Yes. Okay. Let us check what is here. again.
Yeah,
What?
it's working now.
Ah, oh, oh, yes. It's a great relief for me. Maybe, I suppose, something like 5 or 6 years ago, I was teaching this programming in different fractal constructing programs, but after that I delegated it to the other people and I forgot. When I was teaching, there was a great number of various very interesting mistakes because the science of understanding mistakes is a very good science, yes. Very good and special, how to catch a mistake and find it. But now, my ability to recognize mistakes diminished. No mistakes?
No, sir, it has mistake.
You have, so you have mistake, then I come here, please open the windows totally.
This one?
Oh yes. First, second, let us make it great.
We are using it for the first time, so
I know, I know, I already forgot about this, but now it happens that I need it and so I remembered. So here you have a mistake. And which, who knows? Sorry, uncheck. Upon I and K, yes? I and K. I don't understand. But what's about all other matters? You have I, you have K, and you have T.
yes.
You have SIM. Does SIM work? SIM is here.
Showing that pi is invalid when we apply.
What is apply? What is invalid?
Pi.
Pi. Oh yes. You didn't define pi. No, 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 no. It must be defined. Sorry, sorry.
Here?
No, 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 no. This. I touch your phone and I am afraid of it. Yes. Afraid. Pi is equal to multiply arc sine of 1. Why? Sorry. Okay. Now apply all this stuff.
No, we have to change it on the notepad file also, no? Here also?
No, 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 no. This is okay. You changed it and you applied it, right? No mistakes. It's okay. Yes, it's okay. Whoa. It's arrow. Oh, wow. Very interesting. And what is T? Oh, what it is. Very interesting. So can you explain me what is arrow? 1.750. 750.07. This multiplied by I. 1.750 multiplied by 0.007. Okay, so let us make it slightly different. I, let it be I. Where is I? No, no, sorry, sorry. I, okay, I. And here you have open the bracket, open the parenthesis, points and 7, 2 rotations, and close it.
Sir, the bracket has closed here.
Which? Rotation plus rotation, yes? There are 2 rotations, yes? And this, no, rotation,
should be,
no, this
should be deleted.
This should be deleted, and this should remain, yes? Okay.
It started here and it
Finished there, yes. Finished there, no. And it started here and finished there.
Okay.
Maybe no mistake. Oh. Yes, but I is, you have very special I. Yes. Everything returned. Okay. So, did you make a triangle made of arrows? Yes. And could you toggle the vertices so that it will be, can you make it this way? Yes, this is not a problem, yeah? Yes, because you need just to toggle 2, 3 and 0, 0, right? So you are able to make a triangle, and you are able to make any polygon or a polygonal line, yes? Okay, so let us make some polygonal line, maybe this way. Does anyone need this text? Show me the person who needs this text. Nobody needs this text. I will erase it. It cannot be recovered. Who needs? Okay. So let us make some polygonal line. For example, this one. 0. Can you draw this figure? You can take some random vertices so that it looks something like that. You can make it this way. Is this challenge too difficult for you? But you're supposed to ask. It's okay, yes, of course. But can you turn this arrow this side? Yes. I need that all arrows go the same direction. Yes, the same. Yes. Can you do this? Why? Open the program. Open the. It's an editor. No. Open the text of the program. No. Just here. This one.
This one?
Yes. Okay. So you have 0031, 0023. Change 0023 to 2300. And you will see the result. It's not very, of course this is not very good. My fantasy was very, very poor. It's better if you do this way. Can you do this way? Can you draw this star? Oh, I found it. Yes. Sorry. 1 second. One second. Web. Document. Curve talk. So, did you succeed to make a...
Arrow something is...
Yes, this... Oh, you just need to toggle the ends and it will... And here. This is not a problem, but what I need a star. I need to... Are you tired? Yes. Please. Do whatever you like. Best. What is this? What? It is fine, but I want a star.
Square. Oh, star.
Star, yes. I want a star. Yes. A star made of arrows. A star made of arrows. Yes? You succeeded? Wow, wow, okay. And can you make a star made on von Koch curves?
From?
A star made of von Koch curves.
Okay, sir.
Koch curves. So instead of arrows, you need to make von Koch curve.
Yes, sir.
It is very simple.
Okay. Let me try, sir.
You are leaving us.
No, sir.
Not?
I'm going to.
So if you have a success with making a star made of arrows, you need to make a star made of von Koch curves. So put, instead of intervals, put von Koch curves, because it has also endpoints 0 and 1, right? Therefore, you can apply this operator to von Koch curve.
Then we have to define.
What?
Then you have to define a function named co, and then
No. You have a operator for von Koch curve, yes? In some of your programs, you can just copy it.
yeah, I have this.
Yes, you can just copy it and insert in this program. Yes.
Then how can we use it? For example, I have this code for co-curve.
Von Koch curve.
It's a code.
Okay. Oh no.
If I use
No. You don't. It is too much. You have an operator S. Yes. S.
yes, sir.
This is a operator S,
Yes, sir.
and K is S.
S,
S A multiplied by K.
yes, sir.
K. But what is A? No. K is A. What is A?
A is half.
No. Oh. Can you show me where is the von Koch curve? This. Yes, okay. And open. Okay. Koch. Okay. Let us look. When there is K.
Its key is K5.
No, and K5
5
is fifth generation.
yes, the fifth generation.
Fifth generation.
Later, S over 5 into S.
Oh,
S K.
so you write K S multiplied by K. You have S, K is S,
It is K5.
K5. No. So instead of A,
Okay. Instead of A,
no, you write here S.
S.
S multiply, apply. No, yes. So you define this, you copy this S and copy this string.
This line
This line
and this line.
and this line.
Copy.
Yes, and paste it into this program. But no. But you haven't saved, but you need just S. Okay, so where is your
Then okay, that is star.
star? Yes. Okay. Open editor. Oh no, editor S. Insert this S.
Okay, control T, save.
Yes.
And one more was
K
K
is equal S star K.
star K. Correct.
Okay. Apply.
Apply.
Apply. It's applied. So look at K.
So this
No, it's
you
no.
have to apply this S into this.
It's okay. Look at the list of
Yeah, this
object. You have K.
key.
It's okay.
But where is the triangle, sir?
What?
Where is the triangle? We need
Which triangle? There is no triangle. We have von Koch curve.
Yes, sir.
But now,
We need this, sir. That curve.
which
Star.
five? You have the star.
Yeah, I have a star. That is a curve.
It's TT.
Yes, sir. TD.
TT is a star.
Yes, sir.
Yes. And write TTT.
TTT.
Oh, sorry. Can you make this TT? Make an operator. If you delete this arrow. No, if you delete. No. In
It's TTT.
yes.
And double T. If we change that arrow,
Just delete arrow.
yeah,
It becomes an operator.
yeah.
Yes, and write. And okay, but this TT, change its name. Maybe T1.
Okay.
T1. Okay, and write TTT.
TTT
TTT is equal
equal to
T1
T1
star K.
star key.
Okay, apply. Can you explain it to the others? Can you explain